Well, you may be wondering why we're just showing 3 images. Let us look at them again, and this time, say the first word that comes to mind for each image. You'll be given 3 seconds to think of a word. Ready? Let's go! There's a high probability for one of the 3 images you said chaotic or chaos. In which, perfect, you got the point of the images. This leads us into our main topic.
Chaos theory.
Well, what is chaos theory? Chaos theory is a mathematical field which states that nonlinear dynamical systems that seem random are actually deterministic from much simpler equations. Chaos theory is also a concept that a small change can now result in a very large change later. It has many applications in several fields of study, including physics, engineering, economics, biology, and philosophy, which primarily states that small differences can have widely diverging outcomes from chaotic systems, rendering predictions impossible in general. Let's take a look at a second example of chaos theory. This is a population graph, we could say. This graph shows, let's say, for a population of rabbits every year, every generation. The A value represents the average that the population increases per year, and the N value represents the initial population of the rabbits, like the starting value. We could see at 3.3 that the graph really it starts off like 5.9, 5.798, 5.3. It's like kind of varies, but once we get to the 10th generation, it kind of like stabilizes at 8.24 and then decreases back to 4.78 and goes back to 8.24 at 14, and then from there on it really just stabilizes there. 8.24, 4.9, 4.79. It stabilizes right around there. But let's go to a value of 3.6. No, let's go with 3.98. So here, though it's really close to the same conditions, just that the population average really increases a bit more. Never again do we see the same number repeat for any of these points. 3.3, 0.9, 0.24. We never see any of the numbers really repeat ever again. And then once we go over 4, the graph just goes into utter chaos. It just goes negatively downwards forever. But if we were to decrease it back down to, let's go 1.8, we see like it stably increases 3.9, 4.7, 4.6, 4.68, 4.68, and then stabilizes at 4.68. And then we see that as we increase the average increase of the population per year, that it keeps going up and up and up until we see what happens at 3.998. That utter chaos. 3.96 actually seems much better. We see that though like these peaks seem like they're around the same, they never really connect. They never really are the same value again. And for this graph, we see the equation of n1 equals an0 times 1 minus n to the 0. We see that, and then we just we do the same equation, but I just change the n values to match the ones before it. And then for the graph, we just graph the n values. But yeah, this is really chaos theory also at its finest. And what really shows a population of rabbits, since we know that really it matters more on the conditions of like the predators and everything in the surrounding area that the rabbits live in, and that when we see that the population stabilizes, that it really isn't always that it really isn't that true in terms of real life. We don't see like the population always stay the same. We see fluctuations every year or so. Some years maybe rabbit populations are higher than others or lower than others. Another example I'd like to talk about is the weather in general. Chaos theory applies naturally to the weather through the various variables the weather tends to intake. So in this case, as shown, lightning. For lightning to occur, there has to be many variables that have to happen. There's many things that have to happen. The temperature has to be right. Clouds, cumulonimbus clouds have to be in the right exact position to occur. Lightning has to strike in a certain position for this shot to have been taken. And it's just so interesting just to see it in nature. Just to see it out in the natural world. After looking at our examples of chaos theory, let's look back at the history of chaos theory. Edward Lorenz was a meteorologist who developed a mathematical model used to model the way that air moves in the atmosphere. He discovered the principle of sensitive dependency under certain conditions, the butterfly effect, after he made a rounding shortcut, while rounding his numbers to the thousands place instead of using the full number. The basic principle is that even in the entirely deterministic system, the slightest change in initial data can cause abrupt and seemingly random changes in the outcome. The butterfly effect, technically. thank you for watching. Be sure to use all the resources down below, and have a good day.